Okay, let's begin with the study of the mechanical properties. We are going to give an overview of the main mechanical properties of the materials. Why is it necessary to know about these mechanical properties? Okay, many materials must withstand forces, loads, problems, deformations when they are in service. So it's very important to know how much they are going to deform and to which extent they can be broken if we go on with keeping or sustaining the load we are applying. And this is very important because we need to design. This is particularly important when we are talking about planes or bridges or whatever, because we need to be sure that the material is not going to break during the functioning of the system. The plane cannot fall down, or the bridge cannot break while we are passing over it. Okay. And the main mechanical properties are resistance, also hardness, and be careful because what we understand by hardness in our common life and the mechanical concept of hardness are quite different. Ductility and toughness. Okay. First, we need some new vocabulary we probably don't know from other frames or from other fields. So stress, which is the force per unit area of the cross section on which the force is exerted. I apply a force over an area. So stress is this force per unit area, and is the responsible for the deformation I'm going to cause. Strain is the elongation or change in dimensions per unit length. It's the percentual. It's a percentual modification of the dimensions. Young modulus, or modulus of elasticity, is the slope of the linear part of the stress-strain curve. It's represented either by Y or E. The shear modulus is the slope of the linear part of the shear stress-shear-strain curve. So here I have a stress, which is this force per unit area. I have the strain, so the percentual deformation, that can be either in, we'll see the different kind of deformation in the tensile or torsion or shear. Then I talk about elastic deformation. If the deformation I provoke with a load is not permanent, so it disappears as far as the load disappears. And we talk about plastic deformation when it's permanent. So when the load disappears, the deformation still is in the material, so it's not recovered. As long as we are in the elastic behavior, we can understand that the Hooke's law is fulfilled, and so we have this slope of elasticity modulus. This is the load charge. This is unload, so I'm decreasing the stress, and then since the Hooke's law is verified because I'm in the elastic regime, then I have these two expressions which are quite simple. Either stress equals Young's modulo times strain, or the same, but instead of a force, instead of a linear force, I have a torque, and instead of the linear deformation, I have an angle, so distortion. Okay. That we have already seen. If we remember the atomic scale, the modulus of elasticity is the slope of the curve binding force in terms of the interatomic distance, and it will be greater and it will be the greater the stronger the bond. Okay. Why the simplest approach, or the simplest way to think on this topic, is to imagine that bonds are springs. I'm sure this analogy you have seen many times. So when we deform a solid, as well as when we are deforming a spring, if I stretch the spring, so what I'm doing is stretching the bond. The elastic regime would correspond to the regime, to the region in which if I lose the spring, recovers the position, okay, recovers the initial length. And plastic behavior would correspond to the point in which the spring does not recover fully the initial length. So either the bonds recover their initial angle and length, or the bonds stay permanently distorted. Well, we have some main deformation configurations. So let's say, at the end of the day, most of the ways in which I can deform a solid can be somehow decomposed in these different kind of these main deformation configurations. So of course, the two main or two easiest configurations are tensile and compression. Tensile stress is just when I have a material and then I stretch from both extremes. So I pull it out from here and from here. So that means I'm going to produce an enlargement of the material, an elongation of the materials. This elongation would be delta L, and if the stress is this sigma force divided by area, so force per unit area, and the elongation is, or the strain is the final length minus initial length divided by initial length. If that's percentual deformation, it's delta L divided LO. Okay. In the case of elongation of tensile stress, this is an elongation. In the case of a compression, of course, the final length would be less than the initial length. Of course, when I earn either stretching, pulling out, or pulling down, so it's compressing a material, of course you will see here also that there is also deformation in the cross direction, not only in the direction I'm applying the force, but also the transversal dimension. This can be evaluated by this expression. So nu is the Poisson ratio, and then it's minus this strain in the direction of x divided strain in the direction of z, or again in the direction of y and z. So these are the two transverse directions, assuming that I am applying the force in the direction of z axis. Okay. Well, sorry. Of course, there are not only these kind of so simple deformations. I can also apply shear, or I can apply torsion. So instead of applying a force, I can apply a torque. So two forces into opposite directions in opposite phases. In the case of a cube, for instance, then it would be F is applied here, same F is applied here, but in the opposite direction. And then, of course, I'm producing and provoking this kind of deformation. It's like if you have a pile of paper sheets, and then you keep fix the lower part of the pile and push only the upper part. So it's going to be deformed. Then the deformation, in this case, is an angle, which is a gamma, which is delta x divided y. So the dimensions and the change in this dimension is, at the first approach, we assume that this dimension is fixed, does not change, and that is the tangent of that angle. Yep. If we go to torsion, then we have something which is twist simply. You have a bar, or you have a rod, and then you twist it. Again, you have an angle, this is the twist angle, and you have a torque applied, which is the cause for this angle to be to occur. Okay. Also, we could talk about bending. Bending occurs when you have a shelf and you put a lot of books, and so they are too heavy, and so in the central part you see that it's like bent, yeah, literally. Then in fact, this is a mix, or this is a composition of compression and tensile stress, because in this area, when I am applying the force here, it's only this I'm not applying any other force here. When I apply this force here, then what happens is that, of course, this part of the material is submitted to compressive stress, and this part of the material is submitted to tensile stress. The evaluation of the deformation is not so simple in these cases, but I just write here the formulas. In the case of a bar like that, a beam like that, which is a rectangular beam, these dimensions, this is the expression for the Young modulus. In the case of a cylinder, so a rod, this could be the expression for the Young modulus. And this is the delta, is properly the beam, so how much the material is bending. And important is that all these coefficients we have seen are related by a quite simple formula as far as we are working with or we are dealing with isotropic materials. Okay, this is the Young modulus, this is the shear modulus, and this is the Poisson gradient. What happened? We have already mentioned the stress-strain curve. What are the main points or the main features of this strain-stress curve? Here they are represented. This is the region in which I have elastic behavior. In this region of elastic behavior, this is the Young modulus, which is the slope of this curve, or this straight line in this case. The point in which this Hooke's law stops to be valid, then it's called elastic limit. During the time, I still have plastic behavior, but it's not so high. So I define the yield stress as the point in which the deformation, if I come here, this intersection with the x-axis, is this 0.002. Be careful, because these two names are different in English and Spanish. In Spanish, the elastic limit could be here, and there's límite elástico, but yield strength and elastic limit are not the same. Okay, that is the plastic behavior region, and here I have the failure limit. Yeah. And this is the elongation at the failure point. The form or the shape of this curve gives us an idea of the classification of materials according to the mechanical properties. So metal is ductile. We have a long elastic regime, then short plastic regime, and then breaking down. In a ceramic, the elastic regime is relatively long, but then I have no plastic regime practically, because it breaks rapidly, so it's brittle. And then this is the behavior of elastomer and the behavior of the thermoplastic materials. Okay. Well, this is an example. We have an aluminum rod, an aluminum alloy rod with a diameter of 0.05 inches, an initial length of 2 inches, and it's subjected to a tensile stress with loads between 0 and 8,000 pounds. We obtain the values here, these values here in the table, and then we can calculate the stress-strain curve. So here we have the stress, here we have the strain, and we are representing these values here. As you see, here is the maximum load we are applying, and then this is the point in which there is a failure. Why does this occur? Because when I'm since the material is also, when I am stretching, it's also decreasing the cross section, then here there is a decreasing also. This is a change in the dimension. There is a change of relaxation effect due to this change in the dimensions. Okay, we're not going to enter in this point now. And then finally it fails, so it breaks down. Well, related with this point is the fact that we could talk about true strain and stress. When we talk about a strain or a stress, we are referring to for instance, in the case of stress, we are referring to the force we are applying per unit area. However, as far as we are deforming the material, as far as we are, for instance, stretching, as I told you, the cross-section is decreasing. So that means that the real area is not the initial one. So somehow I should have this into account. And to take that into account, we define the true stress in which the area of the real cross-section is taken as the instantaneous area, not the initial one. And the same for the true strain. So we take the actual dimensions taken at each load point. Yeah. So we are going to compare this small exercise. We are going to compare the engineering or stress and strain with the corresponding true values for the rod from the we have for the aluminum rod we had. So this is the maximum load point. And we can calculate this from the data in the table. This is the maximum load point. This is the stress. This is the stress, the true stress. Again, and here if we go to a breaking point, these are stresses, ideal, so to say, and true. And again, ideal and true. Well, you have here just the yield strength and the modulus of elasticity of some families, some groups of materials that you can see that much better if you use this program, this selector of materials you are already working with. And I'm sorry, but if you go to an English book, probably you are going to find all the dimensions in imperial system. So that means you are going to work with pounds per square inch, megapascals or gigapascals, or so. It's important to have this at least conversion table to have it at hand, just to transform from pascals or newtons or pounds or whatever. Okay. Again, we come back to the data for aluminum that we have already used, and then we are going to calculate the modulus of elasticity. So these are the values: load, this is the elongation, this is stress, this is strain, and so in a very simple way we can calculate the modulus of elasticity, so the E or Y, so as you want. Imagine now that a rod must withstand an applied force of 45,000 pounds. And to ensure that we are in a low risk regime, I mean that we are safe enough, the maximum allowable rod stress is limited to 25,000 pounds per square inch. The rod must be at least 150 inches long, but we only admit elastic deformation around 20.25 inches when the force applies. Okay, then we are going to design the rod. Of course, we have our expression. Stress is defined in this way, so that means this is our area for our. So of course we have this 45,000 and 25, which is what we are limited to. So that means this 1,1.8 square inch. Then we have this A sub O, so the area, then it's our diameter, and since we need to have a minimum length for 150 inches, then we need to go for this value here. Okay. Have in mind that we have calculated this value here in this exercise. So this is the value we can have for stress, and so that means that the minimum diameter for our rod is 1.85 inches. Okay, so a little bit thicker than it was considered here. because of this restriction we have applied in the second part of the exercise. Well, there are many more important factors when we are dealing with mechanical properties. And then hardness, I have told you about the differences when we talk about hardness in our everyday life and about hardness in mechanical properties field. So hardness in this context measures the resistance of a material to being penetrated by an object. Yeah. The impact test is also very important, measures the ability of material to absorb a sudden load without breaking. Then factors which are important here in this kind of text are the impact energy, so it's the energy required to produce the impact fracture, and the toughness, which is the energy absorbed by the material under these conditions. Then we can talk also about fatigue. Fatigue is the decreased fracture stress due to the repeated charge-discharge cycles. This is very important in structural materials because, for instance, imagine that I don't know, the wing of a plane. The wing of a plane is submitted to stress cycles every time it flies. Not only because it goes up and down, and so the change in temperature is very high, and so that means that it's going to expand and then to contract again. So that means a lot of fatigue, but also because the winds are quite long, and so when the plane is flying, they are vibrating, and so this vibrational movement is cyclic, and so it means that they are going to be submitted to repetitive charge-discharge or low and low cycles. And this is very important because the fatigue problems can lead to what is called catastrophic failure. Yeah. Then creep is the permanent time-dependent deformation that occurs when you apply a constant load or constant stress. Typically, it's very slow, but over long times it can have some problems. It's very typical when you see, for instance, in pipes. It's quite easy to see. In pipes or in cables, it's also. Then fracture, microcavities, fracture transgranular, intergranular, through microcavities, and chevron-like. Or also very important is the thermal shock. Thermal shock is, for instance, in the plane. When you go up, and then the environment is too cold, so the material contract. And then when you go again to the earth, and then the material expands again because it's much hotter, and so it goes up again and goes down again. So you have this. It can be very rapid, and you can have thermal shock. And surely you have seen thermal shock when you have, for instance, a glass, and it's cold, and then you pour in a very hot liquid into the glass, and it rapidly cracks. Yeah, that's thermal shock. Yeah.